This back side of the page, you start with the number radical 2, which after the events of packet number 1, I think we all agree is not a rational number, right? Square root of 2 is irrational. But then I'm asking you here to use the decimal expansion for the square root of 2, which again is not something we're going to do very much because it's too concrete. Decimal expansions are limiting in a lot of ways. But we're going to sit with it just for today to find an example of a rational number which is within 0.001 of the square root of 2. Okay, that's another way to say what's written here in part C. So some group give me an example of a rational number that you found that was inside that interval. I want to volunteer there. Answer. Okay, so here's the square root of 2 on the real number line, and here is an interval around square root of 2, and the radius of this interval is 0.001. So I'm going to just sketch a picture on here So 0.001 is the radius of this little interval that we've constructed on the real line around the square root of 2. And you're saying that the rational number, 1.414, is actually in this interval. Is it less than or greater than the square root of 2? Yeah, it's a little bit less than, right? Based on the decimal expansion for a square root of 2. And how do we know 1.414 is rational? How do we convince ourselves that it was rational? Because the decimal expansion for it stops. It terminates, right? And you can convince yourself that every terminating decimal always represents a rational number. Okay, so we know based on this concrete example that we can get that close to the square root of 2. Even though the square root of 2 is irrational, we can get that close with a number that is rational. So then what happened in part D? So now in part D, our interval doesn't have a radius of 0.001 anymore. Now the radius is 10 to the power minus 12. So we have a much, much narrower target that we're setting for ourselves. So this time our radius is considerably smaller. 10 to the power minus 12 is the radius of this interval here. So what was an example of a rational number inside that small interval? 213,562,374. And was that less than the square root of 2 or greater than? Sorry, what were the last couple digits? 374. So you rounded that one up? Is that what happened? Okay. So yeah, it's not less than the square root of 2. Is it? They should both work. Yeah, there we go. So if we use 7.3, then we get a number which is slightly less than the square root of 2. If we use 374, we get a number slightly greater. But the point is that it's also rational because decimal expansion stops. Decimal expansion terminates, right? So with those two examples, what was your inspiration in part E? How did you justify to yourself that for any value of epsilon, everybody say the word epsilon. Please don't call it E. Epsilon is our friend and constant companion in real analysis. For any epsilon greater than 0, no matter how small, by the way, every time we write the letter epsilon, usually it comes with this connotation, no matter how small, we're going to use epsilon this semester to represent quantities which can be made arbitrarily small. It tends to be the notation that we use. Can't go too long in a real analysis course without meeting this Greek letter. So how can we know, or how did you explain in your team, that no matter how small I make this little interval, I can always find a rational number in that interval? What were your thoughts? Yeah, well, okay. Well, so part of my purpose on this assignment was to get us to think about this without having the theorem about density in our pocket. We can use the definition of density, but we don't know what is dense in this case, unless we can use that theorem. I mean, certainly if we could use the theorem, then what would the theorem do for us?
So I was thinking in terms of if there's there's an x greater than the square root of 2 minus epsilon, but less than the square root of 2 plus epsilon,
Yes.
that there definitely exists like a rational number between the two that will work, which is why
Yeah. In fact, that is what the density theorem says. Right? The density theorem says that in between square root of 2 minus epsilon and square root of 2 plus epsilon, there exists a rational number. Right? For sure. The density theorem says yes. Let me be a little bit more concrete in this example to finish up. How might our work in C and D be adapted to give us a way of thinking about this using decimals? Huh? So, well, all right, so if E is a decimal of the order of magnitude 10 to the minus k, then
we can truncate A at the decimal place.
Okay. Truncate A to k decimal places. And then I'm going to find that where?
Within.
Yeah, it's actually going to be a little bit less if we truncate, right? But yeah, it's going to be inside that interval, and it's going to be a rational number because it's a terminating decimal expansion. And then the only question is, what in the world do you mean by if E is of the order of magnitude 10 to the minus k?
Yeah, I guess because saying in the proof, like, count the number of numbers and decimal.
Right, so this is the tricky spot, right? Epsilon could be a really small number. Remember, this has to work for any epsilon we choose, no matter how small it is. Right? So if E is really, really small, if it's closer to 10 to the minus 12 than it is to 10 to the minus 3, then I should pick 12 decimal places to truncate. But it's this navigation here, right, where we're taking epsilon, which might even be an irrational real number, right? And we're sort of finding a small power of 10 that's close to epsilon. It's not clear how we would actually do that, but we're going to get the machinery in our third packet in the form of the Archimedean principle that's going to let us make that more formal. But for now, this is the kind of way that we can use our intuition about decimals to get to this result.